Welcome to our explainer on tempering. It's this intense, fiery, metallurgical process that quite literally stops the modern world's steel from just shattering into pieces. I am so excited to guide you through this today. Think about it. We walk into skyscrapers, drive over massive suspension bridges, and rely on heavy machinery every single day without a second thought, right? But have you ever actually wondered how the steel holding all of that together can withstand decades of immense, repeated stress without snapping? Well, it all comes down to a very specific, highly controlled trial by fire. So, let's jump right in. Today, we are exploring the creation of something called Sorbite. It's the ultimate fatigue-fighting structure born deep inside metal. In metallurgy, this is basically known as the dream structure for high-tensile steel. It's exactly the microstructure engineers aim for when they need materials that absolutely, positively cannot fail under pressure. Here's our roadmap for today. We're going to cover 1. The secret to tough steel, 2. Fourth stage tempering, 3. The Sorbite microstructure, 4. Defeating metal fatigue, and finally 5. How all of this builds our modern world. Let's kick things off with part 1, the secret to tough steel and overcoming weakness. We have to start with a fundamental problem. Steel, in its natural standard state, which is often a mix of ferrite and pearlite, is just too weak and unstable to handle repeated, heavy stress. If we just used raw steel for our bridges and bolts, it would eventually just snap under the constant strain. To fix that weakness, we have to put the metal through what I like to call a hero's journey. Step 1 is quenching. Basically, we heat the steel way up and then rapidly cool it. This creates a structure called martensite. Now, martensite is incredibly hard, but it comes with a pretty fatal flaw. It is highly brittle. If you drop it, it could literally shatter like glass. So step 2 involves carefully stepping the metal through several tempering stages. We reheat it to lower temperatures to slowly trade away some of that extreme brittle hardness for flexibility. And finally, step 3 is where the magic happens, executing stage 4 tempering to achieve ultimate toughness. That brings us to part 2, the fourth stage tempering, the critical trial. This is the absolute most critical test of the entire process. It's where we cross the finish line and actually create the structural steel that runs our world. What's incredibly fascinating here is just how strict the temperature rules are. To create sorbite, the metal has to endure very precise heating windows. For high-tensile structural components, think bolts, nuts, and machine shafts, engineers have to hit a temperature range exactly between 500 and 610 degrees Celsius. For heavy-duty springs, which need a slightly different balance of tension, they dial that temperature back to between 450 and 500 degrees Celsius. And missing these strict targets, it's catastrophic. If it's too cold, the steel stays brittle and shatters. Too hot, and the steel gets entirely too soft and warps. It literally has to be perfect. Moving right along to part 3, inside the Sorbite microstructure, a microscopic view. So what actually happens deep inside the metal when it hits these exact intense temperatures? Let's zoom in a bit. During the earlier stages of tempering, the metal contains what metallurgists call fine granular cementite. You can think of these as tiny, somewhat unstable particles just scattered throughout the steel. But when we hit that intense heat of the fourth stage, the heat acts like a massive microscopic organizer. It forces those tiny, fine particles to merge and bond together. They aggregate into a much larger, highly stable structure called coarse granular cementite. This specific transformation, from fine to coarse particles, is exactly what unlocks the metal's hidden superpower. We call this new coarse structure sorbite, naming it after the pioneering British metallurgist Henry Clifton Sorby. And honestly, this brilliantly illustrates the ultimate trade-off in material science. You see, sorbite is actually the softest phase of all the tempered stages. We're intentionally sacrificing a little bit of sheer hardness. But in return, the steel gains the absolute highest toughness and resilience possible. It becomes incredibly difficult to tear, crack, or fracture. Which leads us perfectly into part 4, defeating metal fatigue, the hidden enemy. This supreme, unyielding toughness is exactly what we need to defeat the biggest hidden enemy of structural integrity, and that's metal fatigue. Get ready for a pretty staggering reality check. Roughly 80% of all material fractures in engineering are caused by metal fatigue. Fatigue isn't a sudden, violent break from one massive impact. No, it's the slow, invisible weakening of a material from repeated stress over a really long period of time. Imagine a wire being bent back and forth until it finally gives up and snaps. That's metal fatigue, and it is responsible for the vast majority of mechanical failures. Standard steel completely fails this test, but sorbite, it's practically immune to it. To fight this invisible enemy, engineers use Sorbite to aim for a very specific sweet spot on the hardness scale. That magic number is 45 on the Rockwell Hardness C scale, or HRC 45 for short. The crucial takeaway here is that when steel reaches this exact value of 45, during that fourth stage of tempering, its fatigue resistance is completely maximized. It's hard enough to hold its shape under immense weight, yet flexible and resilient enough to absorb endless repeating vibrations without ever developing those tiny microscopic cracks. And that brings us to our final section, Part 5, Building Our Modern World Safe Infrastructure. By mastering this thermal transformation and hitting that exact hardness of 45, we unlock the materials we absolutely need to build our modern world safely. This Sorbite structure we've been talking about is truly the invisible hero of our daily lives. It's the exact microstructure holding together the high-tensile structural steel beams in the buildings we work in. It's inside the heavy-duty industrial bolts and nuts securing massive bridges. It's what allows rotating machine shafts and engines and power plants to spin endlessly without snapping. And it gives high-stress mechanical springs the ability to compress and decompress literally millions of times without losing their strength. It really changes how you look at the physical world around you, doesn't it? Every skyscraper, every bridge, every engine, they are all a testament to humanity's ability to manipulate the microscopic structure of metal using extreme heat. So as you go about your day-to-day, take a look at the hidden engineering all around you and ask yourself, how many perfectly tempered, Sorbite-structured bolts are quietly keeping you safe right now? Thank you so much for joining me for this explainer. Keep asking questions, and I'll catch you next time.